diseases, sign my name, publish and perish all the same.
So today I'm going to talk about all you need to know and we're afraid to ask about tropospheric chemistry. So before we start, raise your hand if you are a chemist. Okay, a few. Raise your hands if you don't like chemistry. Right, there's a few of you as well, okay. What I will convince you by the end of this talk is that you wish you were a chemist. There's a whole world of excitement that you will be missing by not knowing this stuff. So anyway, I want to really show this school is all about showing you all the different parts that you can put together in modeling frameworks. So I'm going to talk a little bit about the chemistry bit. And tomorrow in my talk, I'll talk about a specific area of science. So I'm going to give you kind of the background material today, and I'm going to talk about air quality as an issue tomorrow. So there's one thing I want you to remember. It's on the next slide. This is all that you need to know about tropospheric chemistry. In fact, it's probably all you need to know about Earth system science, if we're honest. You have the whole of tropospheric chemistry in one slide. The first thing to remember is things are emitted into the atmosphere. And you have lots of lectures about emissions, and people like Claire do lots of really good work on that. And you emit it. Normally, most of the sources, 95% of the sources, are at the surface, and you emit it into the atmosphere. Then you've got chemistry, which will take that and it will chemically transform it normally into something else, that emission. Now, there's an arrow in that, and there's also some transport, kind of meteorological noise that goes along with the good chemistry that goes along in the atmosphere that you have to think about as well. And I'm going to talk a little bit about really this step in today in terms of the chemistry and the transformations that take place. And the third step is that we then lose the stuff out of the atmosphere, and that's normally through processes like deposition. It also could be things like chemical sinks. So this is all you've got to understand. If you remember only one thing from this summer school, remember this. Things go into the atmosphere, normally from the surface. They're changed and transported, changed by chemistry, transported by meteorology, and they normally come out of the atmosphere in some way. Now, this is a process for some molecules that can take place in seconds to minutes. For some molecules, it can take decades and millions of years. So there's a whole gamut of chemistry and physics that take place in the atmosphere. But just remember this one thing. Things go into the atmosphere, they're changed, and they come out again. So, if I was to give you a view of tropospheric chemistry, it looks a little bit like this. You can actually think of the system as a low temperature combustion system. So you think that you put fuel into that system, and I've chosen methane, the simplest hydrocarbon here, and the end product of all the oxidation chemistry that takes place is that methane is oxidized into carbon dioxide and water. Now clearly, as you walk outside here in the beautiful Basque area of France, you don't see flames licking up the street. Well, I hope you don't see flames licking up the street anyway. So this is not a thermal process, as you're used to in a combustion process, but actually it's a photochemical process. So we photochemically oxidize the oxidants that we put into the atmosphere, things like methane, and we convert it ultimately, everything will be oxidized to carbon dioxide and water. They're the end products of the oxidation system in the atmosphere. So here's a little bit more of a complicated thing, but actually this is just beginning to think about, as I take my 3 steps away, how we can break that down. So when we get to sources, things being emitted into the atmosphere, we tend to talk about anthropogenic sources. We often call this man-made. Now I want to make this absolutely clear. Women are involved in this as well. Yeah? We have to thank the Greeks, actually, for this. It comes from man, which is manus, which is, any Greeks in the audience? Good, you can help me out on my Greek if I get stuck. So it means helping or hand. So we don't mean man as in gender. So we're involved here in anthropogenic emissions and also the natural emissions, biogenics. we go into a chemical reactor, and it's that chemical processing that I'm going to help to take apart for you in the rest of this talk. To note at the bottom here, some things don't get chemically transformed. We call those primary emissions. And we often talk about primary pollutants and secondary pollutants in the atmosphere. Primary pollutants are things that are directly emitted into the atmosphere. Secondary pollutants are those that are made by the chemistry in the atmosphere. The most famous secondary pollutant that we're going to spend a lot of time talking about is ozone. But primary pollutants can be particulate matter. But particulate matter can actually be emitted into the atmosphere as a primary pollutant, or it can be formed by the chemistry through secondary organic aerosol or something like that. So you often have to pick apart this primary versus secondary driver in the chemistry. And then there are a whole bunch of impacts, and I believe you've been lectured to death on aerosols, so I'm going to avoid talking about much more about them. But there's also oxidant chemistry and smogs and the like. These arrows here, the lines around my diagram, are to recognize that things are transported in this. You do get some sort of transport factor. And there are some pollutants, like persistent organic compounds down here at the bottom, that are actually just never transformed. You put mercury into the atmosphere, it passes through the different components in the Earth system and partitions between them. Now, what you can see progressively over the last 3 slides, there's been more chemical symbols appearing. But I want to leave you with a strong message here. The fast beating heart of the atmosphere is the oxidation chemistry. So we're emitting again here, and it's this chemistry here with this heartbeat, which is really the heartbeat of the atmosphere. It controls the lifetime of the chemicals emitted into the atmosphere. And that's really, very important because lifetimes of molecules is going to put them in effect. So let me do a little pop quiz. You're all atmospheric scientists of one variety or the other. If I was to put methane into the atmosphere today, how long would it be here for? Pardon? 11.2 years. Oh, that's a very precise number, 11.2 years. 11.2 years. Have I got any other offers? Anybody who thinks it's going to be here for about 2 years? 4 years? 6? 8? 9? 9.2? 9.3? So, gentlemen, I want you to think about one thing. If you break wind in this hall today, it's going to be with us for 9.3 years. There's a very important lifetime. I know women don't break wind, so it's fine. It's a very important lesson there, that molecules have very distinct lifetimes in the atmosphere. So, 9.3 is the latest number, I believe, that I saw in the AC&C MIP recent paper on the atmospheric lifetime of methane. So it's about 9 years is the latest estimate. But 11's not bad. 11.2 is fine. So when we emit these things, and it is this fast heartbeat of the chemistry that drives the lifetime of the molecules, and that's very important. I'm going to skip over that one. It's just another way of saying what I've already said. No, actually, I won't. There are many different oxidants that can control this lifetime in this center here. And I'm going to take you on a tour today. The most famous is, of course, OH, the hydroxyl radical, and we'll come back to its chemistry. But it isn't the only oxidant that can drive the lifetime of a compound that is emitted into the atmosphere. There are halogens. There's chemistry that only goes on at night. This is the nitrate radical chemistry. And ozone itself, which is produced by this chemistry, can react with some classes of molecules. So when we emit a molecule into the atmosphere, its lifetime chemically is going to be controlled by these oxidants that are available. It is actually, in reality, a combination of both the chemistry and the meteorology that controls the lifetime in the atmosphere. But I'm not going to go into that sort of detail today. So, to some oxidation chemistry. Here is the chemistry of forming OH. We take an ozone molecule here. We could break it apart with light, which I've written as a photon here, H nu. We form O singlet D. Now, can't write on anything, can I? Okay. O singlet D is an excited state of oxygen. It's the first excited state of oxygen. Often, if you're not a chemist, you write it as O star, which means it's excited. And the thing about that is actually quite important, because the excited state of oxygen reacts with water to form two of these hydroxyl radicals. And that's in competition with a pathway that can then take it back down to the ground state, which is O-triple-P of oxygen. So does anybody want to guess what the lifetime of the hydroxyl radical is, approximately? So methane, we were at 9.2 years, weren't we, we decided? Or 11.2, depending on how you calculate it. What about the OH radical? Seconds, yeah. It's got a lifetime in order of seconds. Yet, it's that lifetime of seconds which controls the lifetime of methane, which is years. It's a wild and wacky world that we live in. And it's formed from this chemistry here. We break the ozone apart. This molecule O singlet D, does anyone want to guess at any time across the whole of the atmosphere how much O singlet D there is there? About 1 gram. And we can calculate that tomorrow in workshop if you want. Calculate the total concentration of O singlet D in the atmosphere. I mean, it's virtually nothing. It's so instantaneous, it's gone away. So 1 gram in the whole of the atmosphere. And that will form the hydroxyl radical. Now, the hydroxyl radical is very important. It's the major daytime oxidant we've been talking a lot about in this introduction. This reaction here, OH plus methane. It forms other radicals here, which is this is called the methyl peroxy radical. I've spent a long time in my youth looking at peroxy radical chemistry, but I won't bore you. It reacts with other things like CO, OH plus CO, to form this, the hydroperoxy radical. Now, I'm not going to torture you too much with the details of radical chemistry, but we do have to go just beyond molecules are lost by reaction with OH. I mean, that's a very important message. The major loss for many molecules is reaction with OH. But actually, this chemistry also drives some interesting secondary effects. So here, we can look at the fate of these peroxy radicals. They can react with ozone in some form to reform OH and HO2. And you're going to be getting the idea quite soon. Didn't that make that? Isn't it going back to make that? There's some sort of cycle going on here. They can actually react with themselves. So HO2 plus HO2 is quite quick. You can form, and that will form hydrogen peroxide, which is an important sink for this. And similarly, HO2 plus methyl peroxide will form methyl peroxide, methyl peroxide. These are sinks. Probably the most interesting bit comes next. They can react with other things in the atmosphere. And here's methyl peroxide reacting with NO. It oxidizes NO to NO2. Similarly, HO2 can react with NO to form OH and NO2. And the interesting bit is that NO2 could then be photolized back to our old friend O-triple-P, which can then form ozone. Now, you're going, oh my goodness, my head's hurting. This is far too much chemistry for me. Far too much. Let's review the key steps here. We form OH. OH can react with molecules to form these peroxy radicals. The fate of these peroxy radicals is absolutely critical. If there's enough nitrogen oxide around, they can oxidize NO to NO2. The importance of that is that you have a major source of ozone, this secondary pollutant. So the key thing is, if you have enough peroxy radicals and enough NOx, you're going to end up making ozone. Now, we can lose those radicals. A very important radical termination step is OH plus NO2, and that forms nitric acid. What's important about that? Well, nitric acid is an acid. Actually, that's the formation of acid rain. And I'm not going to go into acid rain and how that comes about, but an important termination is if you have enough NO2, you can close down that system and form nitric acid, and you get acid deposition from that system. So back to, there's only 3 things you have to understand. You emit things into the atmosphere, you can react them, they come out. A very strong way of removing these species is actually through nitric acid, which comes out and deposits to the surface, and actually can have an impact on ecosystems. Now, I don't expect you to kind of write down this scheme, and these slides will be freely available on whatever websites required from here. But now, if we look at the oxidation of methane that we've been talking about before, we've got the chemistry up at the top here. We make OH, react it with methane. We now get some cycles. Depending on the amount of availability of NOx, you either get the methyl peroxide radical forming these peroxides, so you don't form any ozone. In fact, you lose ozone, that one molecule that you used to form OH at the top there, you actually lose. If you've got enough NOx, you can go around a cycle here and form ozone. So you've got this balance, a very, very important balance in the chemistry to produce or destroy ozone. And as we follow it down here, you can go out and you can form the same cycle with HO2, the hydroperoxy radical, either by directly forming it from CO or coming out of this chemistry at the top here, and you can get that same cycle, peroxide formation, or in fact oxidation of NO to NO2 and a cycle. Typically, in low NOx conditions, I can put one OH molecule in and it will oxidize somewhere in the region of 6 to 8 NO2 molecules. So it's a catalytic conversion cycle in some senses before it terminates. And you get this balance between net ozone loss and net ozone gain. So they're actually quite important, these radicals, not only OH, they're very important as hydrocarbon oxidation intermediates, they're very important in this tropospheric ozone production, they're also very important in this formation of these gas phase peroxides, which have other qualities as well, some of which are also reactions directly with aqueous aerosols. These radicals can go into the aerosols, but also things like peroxide can be easily scavenged into water-bearing aerosols and act as part of the chemistry. So, as I like diagrams and I like figures, this is what we've learned. This is what I call HOX in a box. I like things, everything has to be explicable in 3 steps. You might notice a certain theme developing through this talk. So you've got a whole bunch of things that it can produce here on the left, and then normally photolysis. So we had photolysis, and I'm not going to go into the nomenclature of how one derives these. We use a little j. It's actually, for those of you that know anything about reaction rates, it's the analogy of a little k, a reaction rate for a reaction. We use a little j for the equivalent first-order photochemical loss process for a molecule. But you can think about it, shining light on a molecule, if you've got enough energy, you break it apart. We write the ozone one as O singlet D because we're particularly interested in the amount of O singlet D. But you can photolyze other molecules here, and there's a range of them on this side here, and there's even a reactive form here. So we produce radicals, and we put them into our cycles here, and we terminate those really in 3 different ways. We terminate them through radical-radical interactions, forming mainly the peroxides. We terminate that chemistry through radical NOx, forming things like nitric acid and other nitrates. Or it is thought, and the jury's out a little bit on this, that you can also have heterogeneous loss of those radicals. So this is my HOX in a box, all that you need to understand. You photolyze, you have the chemistry that goes round, the output of which will come back to the very important question of how much NOx to drive ozone formation, and you could terminate through these 3 routes. And here's a very beautiful example of some radical data taken probably actually it's more than a decade ago now. And actually what you're looking at here in blue is OH. This is in 10 to the 5 molecules per cm cubed, so that's not very much. What units do you like? PPT? That's in the order of 0.1 parts per quadrillion, if you want them in that sort of unit. So not very much. And actually what you're looking at here is the tracking of a solstice, an eclipse. And we can see the red line is the amount of light. This is the J ozone, the photolysis rate of ozone. And you can see that drop away as the sun is covered by the moon. And you can see the radicals fall away. And actually on the top here, you can see the ozone. The ozone starts to fall away because that radical chemistry is no longer making ozone. It's a very cute example here. You need light. We've decided they have very short lifetimes. You can turn that chemistry off with something like an eclipse. And this is what a typical day's worth of these measurements look like. Here's OH. This time it gets to around 310 to the 6. The white line here is the amount of JO singlet D in this case, and you can see the OH. And this is actually the peroxy radicals, the concomitant peroxy radicals for this one here in pink. Peroxy radicals should always be plotted in pink. P for peroxy radicals, P for pink. That's my theory at least. And blue here is the JO singlet D, and you can see the same sort of thing. And there's actually a whole host of information. I could bore you for hours just on this diurnal cycle. There's lots more information. You might notice that the radicals persist longer into the evening once the light has gone away. That's actually because you've got this control by these self-reactions, which are slower. You'll notice that OH is slightly narrower than JO singlet D. But I'm not going to do that. I'm going to show you that these are real drivers of the oxidation chemistry that's taking place in the atmosphere. I want to reinforce a point that I've made earlier with the next overhead, which is the scale of effects. So what I've got on this axis here is a time scale, and I actually stole this picture from a book Guy Besseur, who's one of your lecturers, wrote a few years ago while it was at NCAR. I think this is a great diagram. So on this axis here, you've got time scale. On this axis here, you've got spatial scale. So all the species that I've been talking about are right down here in the bottom corner. So they're acting across time scales of 1 second to the lifetime typically of a proxy radical is a minute and a half, maybe, depending on the amount of NOx. The nitrate radicals we'll talk about a bit later. So they're really very, very small scale. Yet, they act all the way across the different spatial scales, which really spatial scales are temporal scales in the atmosphere as well. Again, I'm kind of ignoring meteorology because it's a little bit convenient, but nonetheless, meteorology superimposes on that. So these radicals here have have effect on all these moderately long-lived species, which go all the way from the micro scale all up to the regional and mesoscale. And you could even get up to some of these compounds, their lifetime, like methane, we've talked a lot about, that cover the synoptic or global scale. So as I've said, we emit a molecule of methane in this room today. It's with us for 9 years or so. So even though radicals seem, very fleeting in the atmosphere, their impact is very much felt. Oh, there we go. So I just want to reinforce this chemistry one more time in a slightly different way, just to kind of reinforce the cycling with you. So here we have ozone, light, and water, and we form OH, 0.2 ppTV in this one. We then convert that to H2. I've not really talked about formaldehyde, so by reacting it in this case with CO, and then we can convert that back by reacting with NO. So we've got that cycle. You form it, you form OH, it goes round quite quickly into H2, and come back round into OH. There are other sources, in this case the photolysis of formaldehyde, but we can also lose it through forming nitric acid or hydrogen peroxide. So what I've actually put on there is the fluxes through this sort of system for about 1 ppb of NOx, and you can see that cycling about 7.3 going that way, 7.1 coming that way. So you can see that cycling. And actually, what you'll see is you could turn over around 1.5 ppb an hour, and that's the global gas turnover rate, typically from this sort of chemistry. And that's given by really this number here, this 7.3 10 to the 6 per centimetre per second. As I said, the recycling to termination ratio, if I pull this apart, how many times it goes round before it stops. So this is essentially the green cycle to the purple cycle here, or the pink cycle here, is around 4 to 6. So you're recycling a radical round this about every 28 seconds, which gives a mean lifetime of this system of around 108 seconds. So there's a coupling in here that's worth bearing in mind. And the key thing, of course, is this oxidation of NO to NO2 to form ozone. Right, so enough fast radical chemistry. Let's move on now. The molecule that keeps kind of reappearing in all this as the important feature is the nitrogen oxides. And nitrogen oxides are incredibly important. Oh, there we go. Where do they come from? Very, very exciting. Scaramouche, Scaramouche, do the fandango. Sorry. Lightning. It's true. Anyone else? Traffic, biomass burning. Anyone else? Pardon? What emissions? Aircraft emissions? Ships? Soil. Yes, I was waiting for soil. Yes. So they're all the major sources. The bulk of it is anthropogenic, from essentially fossil fuel combustion of one type or the other, so power stations or cars. And then going down in order, I think soil is the next biggest. I think, lightning is very variable depending on who you believe. Lightning is a very interesting one because lightning, of course, is one of the few sources that doesn't occur at the surface. So my 95% of sources occur at the surface. The big exception to that, of course, is lightning, which occurs all the way through the height of the atmosphere. So they're very important molecules. I'm going to talk about air quality tomorrow, and NO2 is the biggest health issue facing Europe in terms of exceedances of air quality, even bigger than particulate matter. They're very important in this chemistry because they drive that balance between the production and the destruction of ozone. They are, in some senses, the catalyst for that. They're not a true catalyst because actually they're sunk out of the system as things like nitric acid, but you can think of them at one level as that. And there's a very important ratio that we use, which says that the ratio of the photostationary state, you photolize NO2 here to form NO, and then reoxidize it back to form ozone. The net of this state, the net of this reaction is the null thing. You perturb that with radicals. And a lot of people have looked for a long time about how you perturb the photostationary state and what perturbs it. And the deviation from it can be used to work out what the radical concentrations are. But I'm not going to really ponder on that. It's probably a bit too much detail. Ooh, don't use green on blue. The very important things you've got to think about the concentration of NOx is its concentration defines the catalytic efficiency of that ozone production, the partitioning of OH to HO2, the amount of nitric acid that is formed, and the magnitude and the sign of the net photochemical production or destruction of ozone. So they're a very interesting molecule in the sense that it defines and controls the balance of all this chemistry. Oh, there you go. Actually, I didn't realize I'd done that. Now you can read it. There you go. And you can actually see this important. Often it's referred to as buffering, and this is some data taken from an urban field campaign a few years ago. We're looking at OH on the top again, and you can see OH just carries on with JO single D. At the bottom one here, you can see the HO2, and in the line here is the NO, and you see when the NO is high, actually there's no HO2, and you can see again on this day, so you can see actually it controls and pushes that balance between OH and HO2 from one side to the other and drives that balance that forms ozone. The way that we often look at this is we draw a curve on the net production of ozone against the NOx. Actually, this is quite a complicated thing, and you notice that I've drawn it as a box because actually that curve is a cut through a much more complicated surface. And you might say, why is he now going to try and project chemistry into 3 dimensions? I'm struggling enough with what he's telling me. Why is he going to do it into 3 dimensions? This is the heart of air quality control policy. If you want to control the amount of ozone that is produced here, you have to understand on one axis how that's dependent on the amount of nitrogen oxides, but also on the other axis how that is available, how is that controlled by the amount of fuel or volatile organic compounds that drive it. So just let's do one axis at a time, and we'll get to 3 dimensions in a minute. So here we have the amount of nitrogen oxide going up, and here the amount of ozone that you produce. Now I've talked about this balance between producing and destroying ozone, And you can see that there's a value here, which is often called the compensation point, at which below that you actually destroy ozone. And this is in the units of ppb per day, but you can see a couple of ppb per day if you're in low NOx conditions. And that's the situation that we have often in what we call the background atmosphere, a long way away from sources. At some point, you pass over that compensation point, and essentially, as you increase the amount of NOx, you linearly increase the production of ozone. So there's a linear relationship here. Then at some point here, bang, it turns over and it starts going down again. And that's the point here, point C on my graph, where that OH plus NO2 becomes really important. So actually the efficiency of the system goes down because once you reach NO2, OH has got a choice. I'm an OH molecule, I'm bounding along, and I've got a choice. Do I react with NO2 or do I react with my VOC? Yeah? At some point, there's so much NO2 that I don't even see the VOC. Yeah? And the whole system slows down. Now, the VOC kind of goes in this axis, and what's the VOC? I've suddenly changed from talking about methane, and I started off describing this whole system as a methane-only system. I've now changed it to all volatile organic compounds. So that OH molecule will react with any volatile organic compound and oxidize to form those radicals, which will then drive that oxidation chemistry of NO to NO2. So there's a third axis here in my three-dimensional representation, which is those volatile organic compounds. So the amount of fuel. So you could think about it back to you've got a basic choice as an OH molecule. Do I react with NO2 or do I react with a VOC? Now what drives that choice is how fast I can react, and that varies with from VOC to VOC. Methane actually reacts very slowly, but there's quite a lot of it. Whereas a molecule like isoprene, which is a biogenic compound that may be familiar with some of you, it will react with very quickly. So you can see that really this chemistry is very much dependent on the mixture of those NO to VOCs. And this diagram here, which is called an ozone isopleth diagram, looks at those production rates here and maps them against NOx and VOC. And it's very important. What you can really see here, and if you don't take anything else away from this, from my somewhat complicated explanation of it, take it that these are not straight lines. It's very non-linear. So if you reduce the amount of nitrogen dioxide, you will not necessarily get a linear reduction in the amount of ozone. There's a region here where it is strongly linear, but it's also, when it's mapped with the VOCs, much more complicated. So really, what we get to is a balance between this net photochemical production and destruction of ozone. And that's just the same graph that I've shown you in a bit more detail. So just to reinforce what I'm talking about when I'm talking about the VOC chemistry, it's really on this slide here. I'm just generalizing to say that OH will react with any hydrocarbon to produce these radicals which will go on. Now, the complexity and why we have chemical mechanisms in models is that not everything is methane. The chemistry here can partition between the ability of that radical to form this oxy radical here versus that oxy radical forming a carbonyl product to nature too. So there is depending on chemical structure and nature, the way this mechanism breaks down can be quite complicated. Also, you can get the formation of nitrates and a whole bunch of other things. So that's where, when you get into chemical mechanisms, you get into air quality, and you get into many of the applications in the atmosphere, you need these complicated chemical mechanisms to map out this. But essentially, you've got to remember, I'm an OH molecule, I have two choices. I'm going to react with NO2 and form nitric acid, or I'm going to react with a VOC, and that VOC means I am going to form, at some yield, a radical that can drive this catalytic chemistry around. And what this next slide shows you is exactly the point that I was talking about. This is oxidation mechanisms for different hydrocarbons here. It's for alkanes. And this is the sort of stuff that chemists really love. I suspect you don't. And you can see actually the chemistry gets much more wild and wacky. You get also these very interesting molecules here in some of the chemistry. This is acetaldehyde here that forms these acyl peroxy radicals. The reason why I mentioned the acyl peroxy radicals, does anybody know much about PAN? Has anybody come across PAN, peroxyacetyl nitrate? That's a very interesting molecule because it's formed in this chemistry here. You can react this one with NO2 and it forms a sink. And there you've got a very interesting molecule. You've got a molecule that has the radical moiety on one side and the NO2 on the other side. And that can be a very stable molecule. It's very temperature dependent. The colder it is, the longer it lasts. And it can be transported over hundreds of miles. So you could take this chemistry from the urban atmosphere and you could transport it into the background atmosphere where it dissociates and releases NO2, which should have been removed from the system, into the background atmosphere. Okay, so I've talked a lot about the theory of all this, and I've even flashed some very big chemical molecules past your face. I want to now talk about experimental evidence. So how many of you here are modelers? You have my sympathy, my total utter sympathy. There's a whole world of exciting experimental science that you will never, ever get to do. I can now begin to show you some of my holiday snaps of some of the exciting, as an experimental scientist, some of the exciting places I've been to in the world, which you as modelers will never get to go to. Hey-ho. I'm just going to show you a very old experiment because the point I want to make, rather than seem somewhat smug, which I don't mind seeming smug, but rather than seeming somewhat smug, what I want to say to you is that the very important thing, I guess all you guys will realize as modelers, the key thing you need as modelers is two things. You need a model, and you need data to test that model with. Yeah? Now, most of you try to pretend that data is produced by some mysterious organization other than yourselves, but there are people that go out there and do that sort of thing for a living. I see Lisa at the back, who's got a large-scale organization that goes out and does that sort of thing. But I want to talk a little bit about how you use experimental evidence to begin to challenge those sort of models. And this is from a place in Australia, which I worked at, called Cape Grim, Baseline Air Pollution Station. It's part of the WMO Global Atmospheric Watch, which you probably heard something about, I suspect, if Lisa's at the back, earlier. It's on the northwest tip of Tasmania at 40 South. It's also got awesome sunsets. It's actually one of the places you want to go if you really want to look at unperturbed air. I'm not going to get into what is unperturbed air, because essentially the whole of the atmosphere is polluted. It's changed since we went back to, if you go back to industrial times. But if you want to get today away from very strong sources, Cape Grim is a good place. And you can have a look at air that's come over thousands and thousands of miles unperturbed by man-made emissions. I just want to show you a very simple piece of data, which I always think is absolutely beautiful. This is a daily cycle of ozone on one axis here, which is in the fill dots here, and hydrogen peroxide in the other. And it's a very simple piece of evidence to show exactly the chemistry that I've just been talking about. So the sun comes up and the ozone is destroyed. Now we're in a situation where there isn't any nitrogen oxides at all. Well, if there is, they're there at about the 1 part per trillion level, virtually nothing. And you can see the hydrogen peroxide grow. Now there's a lot more in this graph than just that. There's all sorts of things, interesting things about boundary layers and deposition rates and all sorts of interesting things that you can get out about that. But here's a very simple piece of experimental evidence that shows you the ability to do that. And I think the point I want to make with this chemistry is that we need to challenge the models with data, and I absolutely believe that we're going to challenge the models with data. This is challenging the models with data, and when we did this, really to get the processes right. And so on a chemical level, there's challenging models to make sure that the processes are represented correctly, as well as challenging the models to make sure the chemistry, meteorology, and the overall sort of picture is there. So there's two parts to that. And you have to think very carefully when you're using data and models, what aspect are you challenging the model about? You know, because there's two truths. There's the real world and there's model truth. And you have to really think about how you're challenging. And when you've got chemical data, that really allows you, and you think about it cleverly, you can challenge the models properly. You could do things here, very simple steady state things to calculate ozone budgets here, where you put the chemistry, and you also put some, in this case, very simple entrainment. To get an ozone budget in the surface, you need to be entraining ozone from the free troposphere, as well as depositing it out to the surface. I was just going to kind of give, very briefly, I'm just keeping an eye on the time, I've got about 10 more minutes. I just want to give you very briefly a sort of thing I've been saying all along, well, you know, you've got to, you know, chemistry, let's ignore the meteorology, chemistry, let's ignore what's going on outside. Now, you can't ignore what's going on outside. That very simple example that I just showed you in that chemical model for ozone, the change of ozone with time had the chemistry, this production and loss of ozone, which I've talked about, plus some very simple entrainment of the ozone into the boundary layer and some very simple deposition. It's quite clear that to really challenge chemistry and to really use observations properly, you have to think about all the other things that you need to take into account. I tend to think of it in terms of continuity equations, and it's not a very popular way of thinking about it these days, but I quite like it. So what else affects the chemistry that you may observe? Horizontal large-scale transport, vertical large-scale transport, small-scale turbulence, losses due to deposition fluxes, chemical production and loss terms, the mysterious and wonderful world of clouds. You know, what do they do? You know, what do they do to chemistry? What do they do in general? You know, who knows? And other things, you know, that can be, clouds can be vertical transport, washout, aqueous phase chemistry, and you need to understand where things are coming from, emissions. And that's often brought together. You can write it down as what I call a continuity equation. So the change of concentration with time and all these things here, the components of the wind vectors, a bit of turbulent diffusion coefficient, a fiddle factor for clouds, production chemistry, loss chemistry, and surface emissions. And that actually, in reality, is probably the basis for every model. So every model that you're probably producing is actually really probably just a version of how you represent those things together in a self-consistent mathematical framework. And that's often what you're trying to solve. So we do have to think about all the other things when we interpret the chemistry. We do have to think about all the other things that come with it. So if we do all that, and we bring it all together, what can we say about the global turnover? I'm looking in a global context. Here are some molecules. Carbon monoxide, global emission rate of around 2,800 teragrams per year. About 85% of it is removed by OH, and I'm not going to work my way down the table here, but you can see really there's many compounds here, and they're moved. There's ones down at the bottom here, CFCl3, which is not removed at all by OH, and in fact, that will make it all the way to the stratosphere. And there's a whole other lecture in stratospheric chemistry that somebody should give you at some stage to talk about when these molecules make it to the stratosphere. So we've arrived at the global turnover, and we've arrived at a point where not all molecules are lost by OH. So in the last sort of 10 minutes, I'm going to give you just a very, very brief tour of some of the other things that can remove molecules from the atmosphere. So let's go from day to night. We've decided and we've shown that OH production requires sunlight. So therefore, the concentration of OH to a first approximation is 0 at night. Yet, tropospheric chemistry doesn't stop after the sun goes down. It's like many students, they don't stop when the sun goes down. They carry on all night. Chemistry is just the same. So the molecule that drives nighttime chemistry is called the nitrate radical. It's formed from the reaction between ozone and NO2 to form the nitrate radical. That's a relatively slow reaction. That actually exists in a reservoir. NO3 also reacts with NO2 to form N2O5, nitrogen dinitrogen pentoxide. Well, I just call it N2O5. NO3 plus NO2 forms N2O5. And it's very important because that is a reservoir that pushes it backwards and forwards. And NO3 will react with hydrocarbons to form radicals, interestingly. And it will also react very, very rapidly with NO to go back to being NO2. So there's very much NO there, as in the urban atmosphere, near the surface at least, you can form that. Also, N2O5, it's worth noting, reacts with water to form nitric acid. So one of the major losses of this is another way of making nitric acid and acidifying. Why don't you get it in the daytime? It's rapidly photolyzed during the daytime. It's rapidly photolyzed in daylight. There are some things, it does actually exist in daylight. It's got a lifetime in the order of 5 seconds, probably, on a day like today. And there are some special situations where it can persist into the daytime if you have certain NO2 to NO ratios. So it's a very important molecule at night, equivalent of OH, in that it can drive this chemistry. It can react with a whole bunch of hydrocarbons. It's relatively slow at abstracting hydrogen, the equivalent reaction that you get with OH. OH reacts with methane. It takes a hydrogen atom away. On the whole, NO3 is quite slow at that. Where it's much faster is actually with alkenes and things like dimethyl sulfide, where it can add across the bond there. And you get very complicated and substituted nitrates again as well. But this formation of nitric acid is also very important. So that was 10 seconds on NO3. It's less reactive than OH. This is what they often say, but NO3 is 100 times more than OH is during the day. But it's 100 times more because it reacts 100 times slower. You know? So there's often people who think NO3 chemistry is really important, and I did a whole PhD in NO3 chemistry. They go, wow, but it's 100 times more. But it's 100 times more because it reacts 100 times more slowly. You know, you have more of something if it reacts more slowly on the whole. There's a few hydrogen abstraction reactions, dimethyl sulfide being a very important one in controlling marine emissions. Some of the aldehydes and ketones here, it reacts with quite quickly, but it will also react with double bonds. So actually for some biogenic molecules, it's an incredibly important loss process. And actually there are some parallels in the way that it produces chemistry. So, you know, if you look down here, it does follow the same sort of things. It does oxidize NO to NO2. It's interesting that OH produces these oxygenated VOCs. We talked a lot about aldehydes and ketones. You've seen them appear. The interesting thing about NO3 is you get messed up with having a lot of NO in the system. You end up with these things like nitroxyoxyacetones. So you actually kind of get this coupling of the HOX and the NOx chemistry, and you get this question of it carrying nitrogen again through the system. And this becomes particularly important, actually, when some of this chemistry comes together to think about the formation of aerosols. It is worth noting, quickly, that HO2 here can be formed by this chemistry. And you do see, and again, if you go back to my very diurnal cycle of radicals, you do see sometimes HO2 at night, really driven by HO3 chemistry, sorry, by NO3 chemistry rather than OH chemistry. That's isoprene oxidation. So as a summary, you can see that you can have a parallel oxidation chemistry driven really by the NO3 chemistry. You have a whole nighttime NOx chemistry as well. Very briefly, there's two more oxidants I want to cover before the end to finish off our full story. There's ozone. Ozone is very much the third tropospheric oxidant, and I spent a disproportionate amount of this time in this lecture expounding the virtues of ozone chemistry. But actually, it itself is a funny old molecule. You know, it's a product of the chemistry of the atmosphere, but it's also an initiator of the same oxidation chemistry that drives its formation. It really doesn't abstract at all, but it will add across double bonds, carbon double bonds. It tends to yield carbonyls, carboxylic acids, and esters. It is a relatively slow. If any of you are familiar with kinetic units, 10 to the minus 17 molecules per cm cubed. Just to kind of give you a flavor, OH reacts with methane at around 10 to the minus 14. OH reacts with most fast-reacting organics around 10 to the minus 11, 10 to the minus 10. So this is it's a million to 10 million times slower than the typical OH reaction. Sorry, that was a question. but there is more of it. So for some compounds, it can be very important in the removal of those compounds. It has a beautiful mechanism, and it forms this primary ozonide, and you get this thing called a Kriege intermediate formed here, and whether that Kriege intermediate is stabilized is very important. There's been some very exciting work recently that's been published in Science on detection of the Kriege intermediate, and which has kind of really brought this together. It is worth noting that in this mechanism here, you do end up with OH being made. So actually OH is made by this chemistry, and you get very different OH yields here from different alkenes. So actually there's another mechanism that can then drive the formation of OH, which turns out to be quite important. And this is another mechanism that can also take place at night. You don't need light to drive this mechanism. Okay, we're on our whirlwind tour. The end is in sight. The last detailed chemistry that you'll have to deal with at this summer school is about to come to an end. So halogen chemistry, a very, very brief overview of halogen chemistry. In a way, halogen chemistry is the newest kid on the block. It's always been an incredibly important part of the stratosphere, but it's really only in the last decade or so that we've really understood its importance. Satellites really began to show the scale. This is some oldish data now on BRO clouds. And what you're looking at is Antarctica, which is a very large place. And what you're looking at is, in red here, is clouds of bromine monoxide. Very large clouds of bromine monoxide, which is a halogen oxide, which is formed by a heterogeneous mechanism which oxidizes this hyperhalous bromine acid here on the sea surface to form a bromide, which then can release. And it actually is an autocatalytic type mechanism, so actually it could spin round, and in spring in Antarctica and in the Arctic as well, actually you get these very large explosions of BRO. So in itself, a lot of people are going, so what? This is huge, but it actually doesn't really seem to change the oxidation chemistry of the atmosphere. It's clear that this sort of chemistry can take place throughout the atmosphere, but not on the scale that you see here. So it's turned out to be quite interesting, and a lot of people are now working out what the real impact of that is. It's not only bromine oxides, there's also iodine oxides. Here's some, again, relatively old data from last decade, showing diurnal cycles of iodine monoxide. You find that particularly at coastal sites where there's a lot of organic iodine precursors. They can be photolysed, and they can drive this chemistry. So, I mean, really, I'm not doing this chemistry justice. There's actually some really new data on a molecule called ClNO2, nitrile chloride, which has just come out, which says that chlorine might be important now as well in all this and affect the lifetimes of these compounds. But I just want to, for completeness, say there's a whole host of halogen chemistry that we're now working our way through to work out how important it is in driving the global oxidation of these molecules. And so you can get halogens from a range of sources and their importance. And they have actually a whole bunch of things that they can do, which I'm not going to go through here, which can actually turn out to be quite important. Okay, so where have we got to? So where have we got to after this hour? You're now all convinced of the following. Tropospheric chemistry is very interesting. Tropospheric chemistry is very important. There is a man that's obsessed with ozone who's talked to us for an hour. But hopefully I've convinced you of is that chemistry is important in the way that we think about the composition of our atmosphere. It's important in the way that we think about the control of that composition of our atmosphere. We're dealing with compounds and chemistry that's really linked across all those scales. So when we emit molecules, they will undertake chemical transformation. And that transformation can have deleterious effects in terms of forming more aerosols. It can have deleterious effects in terms of forming photochemical smog. But we've also got to understand this chemistry, because if we are to ameliorate the deleterious effects, we have to understand how, if we change the emissions, which at the end of the day is the only knob that we've got in the system to control the composition of our atmosphere, how that will respond. And to understand that, we've got to understand how the chemistry is, not only on a theoretical level of chemical reactions and rate constants, but how they respond in the atmosphere when we put that together with all these multiple oxidants pulling in different directions. So that's really the message that I want to leave with you. But there's one more thing. There's one more thing that you must not ever forget when you leave this summer school. There are only 3 things that you have to remember. Things are emitted into the atmosphere, mostly from the surface. They undertake chemical transformation, which I've now convinced you is incredibly important. And we've talked about the main routes of those chemical transformations, and they're lost by deposition or sinks. Thank you very much. Do we do questions?
Is there any pressing questions? Because we have also workshops.
Yeah, so are there any pressing questions, anything particularly on the top of your mind after that? Yeah, I mean, I'm around till Wednesday, so if there are any questions. Now, this is your summer school, so please feel free to come and ask me questions. I can bore you to death on a myriad of topics. Thank you.